I'm going to take a little bit of a departure here and talk about, in broad strokes, of research that has been going on in my lab for the past many years, and where this can provide opportunities for the future, and some glaring gaps in the in what's going on in the field. Um, just to give you a little research in the teaching state of affairs, here's my contact information. Myself, I'm interested in developing mechanically enhanced catalysis, which is a term called mechanocatalysis. We use we characterize heterogeneous catalysts for high activity due to the presence of defects. 2D catalysts are actually particularly work well for this because of their interaction with the mechanical force and high surface areas. Additionally, what's come out of my research group is scalable production of chemicals and catalysts, which you don't often see coming out of academics. So we really have an eye on what processes are we developing, what um, syntheses are we developing, and how can they be moved into potentially industrial applications. I have worked with people in mechanical engineering, Jacob Hatt, Subith, Kareem. We do characterization of biodiesel, biojet, and biogasoline fuels. Um, Mechanochemistry itself gives you alternative synthetic strategies, so that is quite useful. In this time at UCF, I've had 19 US patents issued, 12 foreign patents, and actually 2 new patents are in process, which I won't really discuss that much. 4 companies have licensed these patents, and I've had a lot of students flow through my laboratory. Why is mechanochemistry, or maybe you've never even heard of this, and I call it mechanical facilitation of chemistry, and there's actually a reason for that. For many years, there's been a bias against among chemists that is snobbish to say mechanochemistry isn't really chemistry, you don't really know what you're doing. Every new technique has people that just resist it. Same thing happened with microwave chemistry. However, in 2019, IUPAC, this International Union for Pure and Applied Chemistry, listed reactive extrusion as one of the top 10 emerging chemical technologies that are going to change the world. Reactive extrusion is just a continuous form of mechanochemistry. So you're applying shear to induce chemical reactions in a continuous manner. And that's actually the dream of chemical engineers, is they hate batch mode. So if you can do continuous reactive chemistry, that is great for scale up and for sustainable processes. Most recently, the EU initiated a cost action, which is a cooperative, I had this written, it's basically cooperative research among EU nations. And they want to really there's really putting a lot into mechanochemical research. So there's a mechanochemistry for sustainable industry, which is actually industry and people in academia working together to develop more sustainable processes that use mechanical force instead of traditional heating. A much smaller chemical center, phase 1, was recently funded by the NSF, and that's at A&M University. That's the NSF Center for Mechanical Control of Chemistry. It's got some interesting players in it, and so we'll see what they do. This pandemic has kind of been hard. The issue with the current state of the art in mechanochemistry is that if you look in the literature, you will see that they said, I synthesized this compound using mechanochemistry. I just made X, and we use mechanochemistry. The fundamental understanding of the processes involved in getting chemistry to work with mechanical force is still in its very much infancy. So what happens is if you have a synthesis and you let's say you develop a material that's really great, but you have to make a mechanochemistry, it won't see its way into industry because there is not a chemical engineering skill set designed to take that to the plant level. So outside of myself and one researcher in the EU, there are very few works on scalability and design of reactors for mechanochemical processes. I'm going to share with you a couple of the projects, and 2 are with industry, and this was actually NSF funded. And this is mechanocatalysis. So we looked at hexagonal boron nitride, which consists of atoms that are the prototypical Lewis acid and prototypical Lewis base. If you're in mechanical engineering or any solid or any materials disciplined, then you know that if you apply a mechanical force and cause plastic deformation, you can actually induce defects in a solid. And so we do that, and these defects are actually chemically active. And so we found that vacancies in boron nitride, specifically nitrogen vacancies, and this was done in collaboration with Dr. Talat Rahman, whose group did the calculations, and Lauren Tattard, who looked at the surface at the microscopic level. They are highly active for chemistry. So we've been able to actually control carbon dioxide hydrogenation. We just recently had this published. And depending upon the temperature at which we run the reaction, we can get formic acid or methanol, which gives you some interesting possibilities for controlled chemistry. The objectives of this kind of research was to enhance catalytic activity in hexagonal boron nitride, but in particular, talk about enhancing catalytic activity in any material. Now, research is done a lot, they say, and if you mechanically process catalysts, you can enhance the catalytic activity, but not much is done on doing catalysis while you are mechanically processing, while the material is undergoing shear, while the material is undergoing compressive forces, and that changes the surface states and that changes the interaction with molecules. And so we sought to investigate the interaction of these active sites that are occurring during these dynamic processes using DFT, that was Dr. Rahman, TIP enhanced Raman spectroscopy, that was Lauren, Solacit Amar, that's a collaborator at Brigham Young University. And on my side, we developed a mechanochemical reactor to enable flow chemistry. Most mechanochemistry is done in batch mode, which is very hard to sell to a company or to people that want to adopt it, because they really want continuous models. This was actually a long effort, and we're still actually working on it. We have some new catalysis that we're looking at it, and lots of graduate students, lots of undergrads worked on this. In addition, we identified that the boron nitride also does a unique hydrogenation. So what it can do under mechanical forces, we can remove nitrogen from molecules. You might say, why do we care about that? Well, biofuels can have a lot of nitrogen because they are bio-derived, and those are bad when you burn them because you can get NOx's. So that needs to be removed. We've gotten 2 patents out of this and 3 publications, 3 in preparation, and we just recently got this new one out. So if you wanted to check it out, also you can contact me and I can give you a link to that. My laboratory, and this is where the opportunity arises, is I have some contacts in the semiconductor industry, and I was contacted by a colleague there, and they needed some titanium tetraiodide, and they had a hard time finding vendors that would synthesize it. There were some issues with the synthesis. It wasn't very high yield, and they needed quite a lot. They wanted 500 grams of material. So what we ended up doing is I said, well, let's develop a new synthesis for you, and we will provide you with this material. And so over here, this is housed by my laboratory. This is a mechanochemical reactor based on an attrition mill. And we have the capability of pressurizing this to 5 bar. We can heat it up to 250 C and as cold as -40 C. Right now it's not heated. And I'm going to show you something. It's not going to be exciting. Oh, sorry. So let me, so inside this is balls that are being moved around with the reaction components. And I show this, you say, well, what, nothing's happening. If we look over to the right of this image, and I'm going to change my, there we go. This is a reaction product. This is actually very pure titanium tetraiodide from the reaction that we ran in this reactor, and we managed to do 100 to multi-100 gram batches at a time. Still batch mode, but the nature of this compound makes it okay for this. And I tell my students this is good chemistry is not necessarily exciting, especially if you're engineering a scaled up solution. You want it to be boring, but we still get yield. So our objectives were to implement a scaled synthesis of titanium metal and iodine and do it safely. And it worked actually quite well. We were actually able to minimize contamination, which is very important for the semiconductor industry. And our final purity was sufficient for semiconductor use. So this was actually, if you can think about it, it was an industry academia partnership where we had skills in mechanochemistry and mechanosynthesis, and the industry contact was open to the idea. And that's where that's where I really envision this going. We have to get industry exposed to this. This is a very low waste, low energy way of synthesizing materials. Uh-oh, yelling at me. If we want to go a little larger, earlier, a few years ago, I was contacted by a company that was looking to produce graphene materials. This is a company called Garmor. And I developed their core process through sponsored research to produce oxidized edge functionalized graphene. That actually kind of blossomed a bit, and we're doing less. My students are actually happy we're doing less because graphene work is really messy, especially when you're doing a lot of it. And so at Garmor, we developed a low waste process at the laboratory scale. I then worked with them and then helped them to realize a scaled process. So this is about 12 feet tall is this reactor, and it's quite large, 170 liter reactor. Now, this is where really you want to work with industry, and we need to get them interested and perhaps cooperating, because having one of these in an academic lab becomes an issue as you start saying, okay, I want to look at scale up. I want to do large amounts of material. Okay, where do you put all your waste? Where do you put your feedstock? So there's this step going from academia to industry that really needs to be investigated, and we need to develop tools to look at that. One of the tools that we've used in my group in the past is discrete element method, which here's a model of this reactor running at speed, showing the compressive forces. And this actually is running really fast. It turns out they don't want to really run that fast. And it shows the compressive forces that developed during the process. We really want to understand the compressive forces in shear, because that helps us understand, are we going to be able to get the chemistry that we want to occur in a manner that's efficient. This project actually, Garmor is focused on just edge oxygen containing material. I looked at that beyond that, and we managed to add halogens to the surface. So we added chlorine, bromine, fluorine, and iodine. And that actually worked with Masoud Atashbar at Western Michigan University. We found it had good sensing capabilities. And so where do we get here? Well, this is probably the most efficient, safest, and most sustainable way of producing graphene materials. And the fluorinated pathway we got is probably the safest way of producing fluorinated graphene materials. It was a local startup company. They've actually recently produced 1 ton of material for one single customer, and they have employed several students from the university. So there's a pathway from students to university to go into industry locally. So we actually have industry coming to the Central Florida and not just depending upon tourism. We got 3 publications, 2 patents. It gets a little dicey when you work with a company, so you have to be happy with what you get. In the near term, where are the opportunities? Well, sustainable chemical synthesis is a key priority for the US and other countries, especially with stretch on resources. You really want to maximize the bang for your buck in efficiency. And if you talk to anybody designing a plant, if you can give them a more efficient synthesis that takes less energy, produces less waste, they would really like to go to that. The issue is to address their comfort level. If you go to an engineering firm, and I've dealt with chemical engineering firms, they say, we're going to use a mechanochemical reactor for processing 200 tons of material a day. And they say, okay, where are the engineering models for this? We have models for plug flow reactors. We have models for cracking towers. We don't have models for these kind of reactors. And that's really where that gap needs to be filled. But there's some really interesting things you can get in mechanochemistry. We can get enhanced biofuel production. We can make advanced materials. I've shown, catalysis under the application of force is actually different than just static catalysis. And that's not too much of a leap to go from a static system to a mechanically agitated system. A fluidized bed is sort of a mild version of that. But also what really needs to be done, and I'm showing you some work we're just working on here, is if we say screw extrusion, which is continuous process, the issue is there's no laboratory size screw extruder. The smallest screw extruder you can get to do chemistry in a laboratory still requires kilograms of material. It processes like a kilogram of material an hour. That is way too large of a size for doing any kind of testing at a laboratory scale. And so we've been working on developing miniature, and when I mean miniature, I mean miniature. These are, you can see the size of our little twin screw extruder there, and seeing if we can get chemistry that occurs in that to match what's occurring at a larger scale. And that's really useful, is to have benchmarks from each scale so that you can relate the scales. Collaboration wise, I do some discrete element modeling, but I am not a modeler by training. And so it's a tool, not an ends to a means. And I'd love to work with people that actually do discrete element modeling. And what was really interesting for these kind of processes is to actually couple that with finite element models, because discrete element models will give you the forces that occur, but you really want the finite element so you can have fluids moving in there, especially if you're doing a synthesis where the balls are mixing and you're providing force in a solution. Mechanical design and testing, we do some, but the more the merrier. And what really needs to be understood is what's going on at the surface of these shear events. Chemically, what's going on at the surface. Traditionally, this has been just been the purvey of people that do tribological research. They look at lubricants. We kind of have to turn that on its head, and we're looking to enhance chemistry, not to stop chemistry. People that do lubricants really don't want chemistry to happen with the surface. Like I said, the national priorities, the NSF, the EU, and the IUPAC have all acknowledged that mechanochemical approaches have a strong potential to change the landscape of industrial synthesis. But we really need to get the engineering models. This is not going to become a useful process unless there is accurate and valid engineering models to take it to an industrial scale. In a long term, I think, and this is going to be a little bit out there, but I think UCF has the potential to be a leader in scalable mechanochemistry. As I've talked to, there are many people at the university that use mechanochemistry or mechanical processing, but we're not really talking to each other. We're not, working. We're all very friendly with each other, but I think a unified voice could really be could say a lot. If we look at Texas A&M, they have a phase 1, so they have some time to produce, but there's also a phase 2 they're going to be going for. And as they go for a phase 2, they're going to be looking to partner with other institutions. This technique needs to be evangelized. Engineers need to be educated in how this approach differs or is the same from traditional chemical syntheses or traditional industrial processes. Again, tools. Perhaps implement a center for mechanochemical processing to provide test benches for industrial customers. There's always a barrier to entry for new technologies. If there was a place where industrial customers can come in and say, we have a process that we want to test with mechanochemical approach, to have a service like that would be invaluable.
1 minute, Richard.
Okay, I'm almost done. Again, collaboration sought, a discrete element model, the same kind of collaboration before. I think a national priority here is we need to look at developing engineers and scientists that have a skill in mechanochemistry with a mindset towards how it is used and how it can be applied in a logical manner. And we need a demonstrable scalability that will enhance the adoption across a variety of industries. Look for improved resource utilization, higher profit, lower waste, lower energy, higher profit. That's really the motivating factor to get this out and being used. I'd like to acknowledge the NSF has funded the boron nitride work. The Department of Energy funded a bit as well. It was basic energy science with Dr. Rahman. The groups I've been working with, the Blair group, the Rahman group, the Tattard group. There are many people across the university that I have worked with, National Science Foundation, U.S. Air Force, and industrial partners. St. Gobain Ceramic Materials has actually been very interested in the boron nitride work we've been doing. Integris gave some interesting motivation for doing a case study. And Garmer Inc. actually, it's great to have Garmer because you can point to them when they say, where is mechanochemistry being used? You can point to Garmer and say, this is an industrial application of it, which really helps as a talking point. I'd like to thank you for your time. And if there's any questions, if we have time, I'd be happy to take any.